Okay, in this video, we are going to discuss center of mass of a regular shaped continuous mass distribution. For example, let's say we have a lamina circular disc, you can say, and it is homogeneous. Homogeneous means mass is uniformly distributed. So, homogeneous. Okay, so in this case, where will be the center of mass for this disc? And this is its geometric center. So the center of mass will be at its geometric center, whatever be the center of this disk. Okay, let's take another example here. Let's say we have a very thin rod, and this is also uniformly distributed mass. So in this case, whatever be the middle point of this rod, we can consider that middle point as center of mass. How can we arrive at this conclusion? So we can do it just by making an argument. Let's say we have chosen this axis and this is, let's say, x-axis along this. Okay, so if we are choosing here an elemental mass, okay, this is, let's say, x, and if this is uniform distribution of mass, there will be, let's say this is dm, there will be another dm on this side exactly at the same distance x, but towards the negative side. Okay, then these two, and yes, there are many more pairs. If you are choosing here, let's say you are choosing another dm1, let's say you have another dm1 here at the same distance but in the opposite side, and you can conclude using this thing. If you have two equal masses, you can say that center of mass will lie exactly in the middle, that is between these two masses. So in the same way, you can just divide all these elemental masses into two pairs, one on right side, another on left side, and you can make this argument and you will come to this point, and this point is your center of mass. Now, let's take another example. If you have a square lamina here, let's say this is a square. Okay, and this square is homogeneous. Homogeneous means, once again, I am repeating that mass distribution is uniform. This is a square lamina. Lamina means two-dimensional thing, plate-like thing. So whatever be the middle point of this square, this point will be the center of mass. So in the same way, we can arrive at conclusion if we have some regular shape objects and those are having continuous mass distribution, or we can say homogeneous, we can arrive at conclusion that their geometric centers are the centers of mass. Okay, now let's take examples and then we will end this. So we are going to take two examples here. Example 6.2, find the center of mass of a triangular lamina. Okay, this is our triangular lamina. Let's say this vertex is A, this is B, and this is C. So how can we find out the center of mass of this triangular lamina? So we have to make an approach. We can divide this triangular lamina in very fine strips. We can divide it in very fine strips. So to keep it visible, I am taking this lid. Otherwise, you have to consider that these strips are very fine. These strips are very fine. Okay, so we can take one strip here to analyze the situation. And if it is, let's say this is a very fine strip, very narrow strip, so that we can consider these sides to be almost straight. Okay, so in this case, where will be the center of mass? So the center of mass should lie just here in the middle of the strip. In the same way, for all other strips, the center of mass will lie in the middle. So let's take it up to lowest level. Okay. So for each and every strip, the center of mass is lying on the middle, and then we can say the center of mass of this lamina should be along this line, which is passing through its middle. Now, we can apply the same approach to other way also. Means we can divide this triangular lamina into several strips. Let me take another color here. It will be nice to see in different color. So we can take these strips along this direction. And then we can say that center of mass should lie along this direction, along this line, which is passing through the middle of each and every strip. And we can make another from here, from this vertex also. So in all the three cases, we can combine that. In first case, we found out that center of mass is along this line. In second case, we found out that center of mass is along this line. And in the third case, we found out center of mass is along this line. So where these three lines are meeting is the point where center of mass lies. Now, this is centroid because these lines which are passing through the middle are the medians of this triangle, and these medians are intersecting each other at a point which we call centroid. So the center of mass in this case is at centroid. Now let's take another example and then we will end this video here. Okay, here we have another example, 6.3. Find the center of mass of a uniform L-shaped lamina, a thin flat plate, with dimensions as shown. The mass of the lamina is 3 kg. Okay, so here we have given the diagram. Now, from here to here, it is it is 2 units. So in between here, it will be 1, and here it will be 1, and this is half. So this is 1 by 2, and this is also 1 by 2. This is 1, and this is 1 by 2 plus half, that will be 3 by 2. And in the same way, if this is 1, this is 3 by 2. Now, so we have to find out center of mass of this thin lamina. Where is the lamina? Let me find out this first. Look, this is L-shaped lamina here. So what we have done, we have just bifurcated this length here, and another bifurcation has been done here. So this lamina becomes a combination of 4 squares, and we know these 4 squares have their geometric centers C1, C2, and C3 as given here. So these 3 will be centers of mass for these 3 squares respectively. So this entire two-dimensional question, means a kind of continuous mass distribution, has been now reduced to a discrete mass problem like this. Now we have 3 point masses and with their coordinates given. So how can we find out coordinates? So this is C1. C1 is at, look, 1 by 2 on X side and 1 by 2 on Y side also. What about C3? This is 1 by 2 X coordinate, and Y coordinate is from here to here, that will be 3 by 2. And then what about C2? We can write its coordinate as X 3 by 2 and Y coordinate is 1 by 2. 1 by 2. And now this lamina has mass 3 kg, and we have distributed this lamina into 3 different squares of equal size, and obviously if it is uniform, then these masses will be equal. So these 3 masses C1, C2 and C3, these are 1 kg each. And let me redraw this situation and then you will find it very easy. So, okay, so we have 3 point masses now, and these 3 point masses are located as given here. This is x-axis, this is y-axis, and let's say one is here, another is here, and yeah, there is one more here. So its coordinate is 1 by 2 for x coordinate, and y coordinate is 3 by 2, and here 3 by 2 and 1 by 2, that's good, and here 1 by 2, 1 by 2, and now each has mass 1 kg, 1 kg, 1 kg. Now you can easily find out what is x of center of mass here. That will be m1 x1. And look, everywhere mass is 1. So m1 is 1 into x1, which is 1 by 2, plus m2 x2. What is x2 here? Let's say this is point 0.2. Let's say this is point 0.1, this is point 0.2, and this is point 0.3. And let me check whether it is the same or not. So yes, this is C1, this is C2, this is C3. So we can write it. So we have x2, 3 by 2, and plus 1 into x3 here, 1 by 2. And then m1 plus m2 plus m3, that is total mass. We can write it directly here. So I'm not writing kg everywhere, unit. And because ultimately it is going to be cancelled out, because we have kg on numerator side and we have kg on denominator side as well. Okay. Hmm. Let's continue here. So this will be 1 by 2 plus 1 by 2, that will be 1. And let me write it a little ahead. 3 by 2 plus 1 by 2 and whole divided by 3. And then 1 by 2, 1 by 2, that is 2 by 2, which is 1. And then 1 plus 3 by 2 divided by 3. So we will have now 5 by 2 divided by 3, and then it will be 5 by 6. Okay, so we got x coordinate of center of mass. Now what about y coordinate? So y c m equals to, look, I'm not writing 1 and 1 and 1 again. So I'm writing directly m1 into y1, which is 1 by 2, plus m2 into y2, which is 1 by 2, plus m3 into y3, which is 3 by 2, and whole divided by 3. And look, this is again coming the same thing. So ycm is also 5 by 6. So we have now the center of mass here somewhere. This will be how much? 6. This is 5. So you can write 0 point, and then it will be 50 and 8. So it will be 48, then 2, then 3, and 3 continue. So 0.83, both x coordinate of center of mass and y coordinate of center of mass, both are 0.83, 0.83. So it will be somewhere here, and coordinate will be 0.83, or simply we can write 5 by 6, and simply we can write 5 by 6 and 5 by 6. So this way, let's get back to the actual diagram here. So this way we can write the center of mass is here. Okay, I'm using some different color. Let's try this one. So the center of mass will be here. Here. And this location is 5 by 6, which is slightly less than 1, as we have 1 here and we have 1 here. So this location is, means coordinates for this location is 5 by 6 and 5 by 6. So this way we have found out the center of mass for this particular problem.